Good morning, everyone, and welcome to Engineering Tomorrow's Clean Water Event Day. We are so happy to see you here on the screen and have you with us. We're going to have some fun today, learning and failing and trying again, right? And building those filtration systems. And I brought along some brilliant engineers who, hey, just happen to all be female. Just saying. So we are going to have a good time. If you could turn those cameras on if you're able, we love to see you. Every now and then we may ask for a wave or a thumbs up just to let us know you're with us. And we're going to go ahead and get started. Good morning. All right, I will turn it over to our amazing engineer presenter, Miss Lauren Sawyer.
Hey guys, I'm so excited to kick off the Clean Water Lab Day. So let me get started by sharing my screen. And we're going to start with introduction to the lab, and then we're going to send you guys on your way to your breakout rooms to actually try the lab. It's a really fun one. All right. All right, so can everyone see that? We
Yep,
good?
yep.
Awesome. So welcome everyone to the live Clean Water Lab Day. I'm super excited to be talking to you guys about this lab because if you couldn't tell my background, my job is all about water. So I do ocean and underwater vehicles for engineering, but I'll get into that in a little bit. But basically, I love water. I love the filtration system, and chemistry is just really, really awesome. So we're gonna kick off this lab. All right. So when was the last time you guys thought about your own access to clean water? It might have been this morning when you grabbed a cup of water from the sink, or from maybe you guys have a filter inside of your fridge. Or maybe it might have been when you guys traveled to a different country and you had to think, oh, can I drink the sink water, I know a lot of people hear about in different countries, you can't always trust their tap waters because of the water filtration. And so we're actually going to consider what it takes to filter that water. And you guys are going to learn so much about the process and a little bit about the chemistry involved in water filtration today. And I know I've been bringing up chemistry a lot, and you're like, this is an engineering company. This is an engineering lab. What do the two have in common? But engineering is really the encompassment of all of the sciences. So, like for me, I do a lot with marine science, how things move underwater. It's got physics involved. Engineers use chemistry, biology, all of the sciences can really come into play with engineering. So this is one that's going to be a little bit chemistry heavy for all of those people who might be really interested in chemistry or don't know they're interested in chemistry yet. So in today's breakout, we are going to explore the water treatment process. We're going to consider how we contribute to our water footprint on this earth. We're going to learn the steps involved in water treatment. And then you guys are actually going to have the chance to design and build your very own water filter. You're going to see in real time water going from super murky to hopefully super clear. And we're going to talk about the process. You're going to ask questions to our amazing college mentors. So before we begin, I want to give you guys a little bit of a background about me. My name is Lauren Sawyer. I am a research engineer at Leidos Innovation Center. It's a big research and development company. And basically, my job is to build things that don't quite exist yet. So I focus on that very edge of science and engineering where we push the boundaries of sci-fi and say, what if, what if this thing existed? How can we get there? How can we make it exist? And my whole focus is underwater navigation. So I focus on vehicles that swim underwater, whether they're manned or unmanned. So think like submarines or unmanned submarines, things that we just send off and they drive themselves. And with unmanned vehicles, we have this issue of how do they know where they are in space and time? And that can be a really big problem because GPS isn't available underwater. So my whole job is to find out other types of sensors that we can use to figure out where we are in the ocean at any given time. Much like you guys have your phones with GPS, we have to find all those alternatives that we can give to the vehicle so that it can report back to us where it is. But that's enough about me. Let's continue on with our lab. I want to highlight real quick to the Engineering Tomorrow curriculum who and the people who developed it. So huge shout out to Muna Dowd and Caroline Gillespie. These are the mentors, the college mentors back when they were in college who helped develop this lab. And the engineer who helped develop this lab is Edgar Martinez. So they did a wonderful job. I hope you guys are going to enjoy it. And now we're going to jump into the actual content. So if I could get just like people throwing their hands up, throwing a number up on their hands in the classrooms, how many times have you guys used water today? See, we have people throwing one. I think I see a one. I personally used water 5 or 6 times today. Brushed my teeth. I took a shower. I've drank 2 cups of water. I made coffee. My dog had to drink some water. So there are all kinds of uses for water in our daily lives, and we use a lot of it. So you may not even realize how much water is used to produce the goods and services that we consume, but that total amount of water is called your water footprint. So I guess the question is, where does all this water come from? How clean does it have to be for all of our daily consumption? And do we have enough of it? And we're going to explore these questions throughout this lab today. So in terms of do we have enough water, although the Earth is covered with over 70% of the Earth's surface in water, most of that is ocean water or super, super salty. It's actually 35 on average parts per thousand salt per water. So that's like just dumping a huge amount of table salt in your water. And it's really, really bad for our bodies and for our on land ecosystems. And the ocean has adapted for millions of years to thrive in that salty environment, but us not so much. So out of all of that 70% of water, only 3% of water on our planet is fresh water. And actually, most of this is stored in glaciers and frozen up in the North Pole and the South Pole. So a lot of it's not even accessible to us. So we have to figure out how to use the water that is available to us and how to recycle it, pass it through so that we can keep using that water that's available as it gets dirty, as it runs through, maybe our ecosystem. It can run down mountains. Rivers are fresh water, but I wouldn't recommend drinking straight from a river. It's pretty filled with bacteria. So we have to figure out a way to clean this water so that we don't get sick by drinking from it. So because we can open the faucet and get clean water, we often forget that water scarcity is one of the grand problems that engineers are trying to solve. And a lot of us are super lucky because we have fresh water available to us right next to our houses. But I live out in San Diego, California, and fresh water is a really big problem. I'm sure the people from Arizona and New Mexico are also, understand the same boat. We don't have a lot of fresh water sources. So we have to either pipe water in from other areas where there are big lakes and rivers, or we have to figure out how to use the water around us very scarcely and make sure that we focus on, using what we need, but not using too much. So we've got a few questions, and I want you guys to think about your answers as I go through this presentation and see if you are correct in what you think your guesses are. So the first thing is, how many cups are in a liter of water? How many cups are in a gallon of water? And then how much water does it take to make your morning latte? So I'm going to give you a quick second to think about your answers, and then I'm going to cycle through and reveal them. All right, so it's in cups to a liter of water. It's a little bit more than 4 cups. And then 16 cups of water are in a gallon. And this one is crazy. It takes 801 cups of water to just make that simple 16-ounce latte. And many of us don't realize how much water is used to produce a cup of coffee, but you have to go all the way back to the beginning of the process and understand that We need water to water the coffee plants that are producing the beans. You need water to produce the actual materials of the cup that you're drinking out of. And then water is used to process and deliver the beans. The beans have to be washed and then they're roasted. And then the actual delivery, you need to produce water to, you know, feed the truck driver that's going to ship the coffee to the actual coffee store, and then the actual water that gets dumped into the coffee pot as it's making that latte. That's the last 16 ounces that go into generating your morning latte. But it's a lot of water just to produce that 1 cup of coffee, and the list goes on and on for even more than what I've just mentioned. So, working to reduce the use of water in producing the goods and services we use is a problem that engineers are working to solve, reducing our water footprint. So I'm going to play a video for you guys, and it's going to talk about, just let's solve water, the kinds of problems that we face with fresh water today. And I want you to think about, while you're watching this video, what are 3 things that you learned from this video, and what are some ways that you can lessen your water footprint? So I'm going to go ahead and play this. Wasn't expecting that. So sorry, guys. 1 second. All right, I might skip the video right now. Sorry, everyone. I don't know
Not
why
a
it's not.
problem.
There you go. It's rolling.
Oh, it's working? Awesome. I don't hear it. Is it still rolling?
No.
Okay, let's skip the video. I'll just talk about what the video. Sorry, everyone. Wasn't expecting to be asked if I'm a bot this morning. So only 3% of the water on this planet is fresh water, as I've already mentioned, and very, very small percentage of that 3% is clean water. So most of it's not even clean. We can currently only mass filter clean water. That means we can't filter salt water in mass levels yet. And there's a lot of research going into filtering salt water like ocean water, which would help coastal communities like San Diego. But the biggest issue with filtering salt water right now is actually the fact that what's left over is this highly salty, concentrated, what's called brine. And like I said, salt water is about 35 parts per thousand salt per water. And this brine is much, much highly concentrated. So it might be, 50 parts per 100, or, 1 part per 1 part water. So it's much more highly concentrated in salt. And we're going to generate a lot of it to generate the amount of clean water that we need to feed a community or supply a community. And so we can't just dump that back in the ocean, because then we're throwing off the chemical balance of the local ecosystem. All these animals that are highly attuned to that exact, 35 parts per thousand salt concentration. Well, now it's going to be much, much more salty, and they can actually start to shrink in size because the salt concentration, they're trying to even it out with the water around them. And so it actually affects their skin, their organ concentration. Some animals, if the water is too salty, their organs fail. So we can't just throw that back in the ocean. So the question is, we have the technology to perform this reverse osmosis on the salt water, but it creates so much waste that we're not entirely sure where to put that waste. So that's the biggest way that, or the biggest challenge that we face in terms of getting access to more water. All right, so now we're going to talk about what contaminates water. And water is called the universal solvent because so many materials can dissolve in it. So if you look at the actual molecule of water, and here's that chemistry coming in, it's a polar molecule, which means that there is a positive charge on one end and a negative charge on the other end. And that's why so many materials can dissolve in it, because it attracts materials of different charges, materials that are also polar, and it can attach to the water molecule and create a brand new molecule. So they'll bond, and now it's created something that is a solution, which means it's completely dissolved, and there's no, if you looked at the chemical composition of it under a microscope, you wouldn't see the individual components that you threw into the water, you would just see a brand new component. Whereas a mixture is more like a salad where you can pick out the lettuce, pick out the tomatoes, pick out the carrots if you don't like them. So that's why water is called the universal solvent, because of that polar quality to it. And on top of that, water is needed for life. So a huge part of our ecosystem consists of organisms which both live in water and need water to thrive. All of these things make water a particularly challenging material to clean up for human use. We can think of three general categories of things in water that need to be removed to make it safe for human consumption. So this is the part of water that we actually can separate. So it's parts of the mixture of water. And the first one is suspended solids. So if you look into a glass of murky water, you can maybe pick out things like dirt, sand, living things, leaves, branches, anything that will give your water color and make it look murky. And this is what we're going to be focusing on in today's lab, those suspended solids, things that actually have a finite size that we can pick apart with filters. There's also dissolved materials, which are things like salt, sodium chloride. This is more like what we find in the ocean. There are metals that are actually dissolved in water that feed other organisms and they provide nutrients for the water ecosystem. And in order to break those apart, you have to actually break the chemical bonds, the ionic bonds of those elements to the water. So there are so many ions that are stable in water, including, like I said, mineral components like calcium, magnesium, potassium, as well as metals like iron and lead. Many dissolved materials that exist in their ionic forms in water can be harmful to people, with a tragic example being the lead from pipes in Flint, Michigan, which dissolved in the drinking water. So you need a much stronger filtration system to break these ionic bonds. And dissolved materials can be removed by many different means, depending on their chemistry, some which directly inhibit their flow through a barrier, such as reverse osmosis. Sorry, everyone. And that basically pulls water through a barrier, and it only lets the water pass and not all of those dissolved metals. So it breaks the bonds of all of those dissolved materials. And then there's also methods called softening, which removes the mineral ions. So hard water is water with a lot of minerals dissolved in it. So softening the water is another chemical process which removes all of those minerals. And then the last category is microorganisms. And this is the one that we, as water filtration scientists, we have to make sure that we remove all of the bacteria that can be harmful to humans. So we have a lot of bacteria in our gut, but some of it's healthy and some of it's not. And some of it can cause sickness in humans. So we have to make sure that we remove the microorganisms in the treatment process. And this can be done by killing the organisms, making an environment that's toxic to them so that they can't survive. So like putting chlorine in water, you might connect this to pools. Public pools have a lot of chlorine in them, and that's to actually disinfect the water so that we can all, play in it without a huge spread of bacteria. All right, let me see if this video works. Perfect. All right, so that gives you a really good idea of the multi-step process that it takes to treat water. So it's not just as simple as, maybe if you're camping, you think, oh, I'm going to boil this water and then I'll drink it and it'll be fine. If it were that easy, we'd have access to clean water for days. But unfortunately, it is a very scientific heavy and multiple step process that takes a considerable amount of money, time, and resource planning. So we have to figure out, where are we going to treat this water? Where is the physical space that we're going to block out for water treatment? And who are we going to hire to actually test this water? So it takes a lot of planning. So in today's Clean Water Lab, you guys are going to be focusing on the filtration aspect of the water treatment process. So that's the part that I mentioned with all those dissolved particles in there, or not dissolved, sorry, floating and suspended particles in there. And you're going to work on separating the water from all of the particles that are in it. And so this is the non-chemical part. This is the physical part of the water filtration process, because this allows us to use materials like rocks, sand, coffee filters, cotton, etc., instead of chlorine or anything that's a little bit stronger and not as easy to distribute in mass to classrooms. So you guys are going to basically build your water filters and see how much of that dissolved material you can filter out. And the way you're going to figure out how well you've done is how clear the water is at the end of your process. So you should start out with some really murky water, and then it'll be super clear by the end, or that's the goal at least. So we're going to review the fundamentals of filtration and explain the design challenge, which will be to design, build, and optimize a filtration system to produce the cleanest water for the lowest cost. So we're also going to look at a cost factor. It costs about $5 to $10 to filter and or desalinate water. So as explained in that video, engineers use an iterative process when designing a product or solving an engineering challenge. The process is iterative, even in each of the different phases. Each time we learn or design, we are constantly asking if we are meeting our customers' expectations. It's also important that we balance quality, cost, and schedule, so we don't want to deliver something super late and the client gets angry. To spark your ingenuity, what if you were the environmental engineer who needed to develop a clean water system that could be used instantly at a very low cost? These constraints are important to the design process. 3.575 million people are dying each year from water-related disease. Our current water crisis is one of epic proportions. Both the LifeStraw design and ceramic filters use the filtration process and mainly natural materials to provide clean water in a timely, cost-affordable manner. So you guys are going to be focused on this learn box right now as we go forward in this presentation, and we're going to learn about what it takes to create a filter. And then by the end of the day, you're going to design, build, and test. And then we're going to go back to design and build, hopefully, if you guys can have chances to iterate on your design. So let's talk more about filtration. With that 3.5 million people dying each year from water-related disease, our current water crisis is one, as I said, of epic proportions. At any given time, half of the world's hospital beds are occupied by those suffering from illness brought on by limited access to safe drinking water, poor hygiene, and sanitation. Granted, these harrowing realities plaguing our society, it's imperative that designers, inventors, engineers, and visionaries do what they can to find a solution. LifeStraw is a small cigar-shaped tube packed with some truly innovative engineering. This clever design purifies water from potential pathogens like typhoid, cholera, dysentery, and diarrhea, all little bacterias, all before reaching your lips. The LifeStraw is an inexpensive way to deliver potable water or drinkable water to those in need, and it is considered an icon of humanitarian product design. So for ceramic water filters, which is the other half of this slide, we get inspiration from nature. Cambodia has ceramic water filters that are deployed, and these water purification devices made and distributed by Cambodian nationals resulted in a 50% drop in diarrheal illness since they were first employed back in 2002. The filters are made from fired clay, and tiny pores of the ceramic material are small enough to remove virtually all bacteria and protozoa, which is a single-celled organism. The design uses gravity to facilitate the filtration process, resulting in a flow rate of 1 to 3 liters per hour. And flow rate is something that you guys are going to be focusing on, especially in your designs, because you might have a great design that's super clear, but the flow rate is very, very small, which means that you maybe get like a couple drips every minute. And so you want to balance that flow rate with the clarity of your water. So if you want to get more into designing a multi-step water treatment process, let's use some common materials to create the settling step. As you saw in the video of the water treatment process, water filtration is an important step in water cleaning process. It's the process of removing or reducing the concentration of particulate matter, or that suspended material, including suspended particles, parasites, bacteria, algae, viruses, and fungi, as well as other undesirable contaminants from dirty water to produce safe, clean water. And all of these things live naturally in, say, like river water or lake water. That's their environment or their habitat. So we want to purify the water so that we can access water from these lakes or rivers and natural sources. What you will be doing in this lab is a specific type of filtration called multimedia filtration. As shown in the picture, this is a water filtration through a vessel that contains layers of different materials to trap the solid material as dirty water moves through your filtration system. As shown in these diagrams, dirty water enters through the inlet at the top of the container, passes through the layers of filter materials, and then clean water will exit from the bottom of the vessel, which for you guys will be a water bottle. You'll be modeling this process today, but on a smaller scale using that water bottle. So now we're going to talk about the lab overview. So water filtration is an important step in the water cleaning process. And so now think about what industries use the process of water filtration. And I want you guys to type in chat if you have access to it. Maybe just think about it in your head. Let's see what comes up in chat. Anyone have any ideas of what industries use water filtration? All right, I'll give you guys a hint. I'll throw an easy one out there. The beverage industries certainly use water filtration. So Coca-Cola, any kind of tea, beverage, or coffee, they definitely need a lot of water to just make their product itself. So soda is part water and part sugar syrup, and then that's carbonated. Any other ideas? Other industries include electronics. You actually do need a lot of water to either power the charging facilities or to actually create the electronics themselves, because they're made of different materials that actually can be found in water. You've also got steel and power generation. And then a surprising one, pharmaceutical and cosmetics. So the makeup industry also uses a ton of water. So you need water to both create whatever makeup you're using, and then usually they have some concentration of water. Think like lipstick or anything that's not a powder would have some concentration of water in it. And then the fields of engineering that are involved in the process of filtering water include civil engineering, environmental engineering, and chemical engineering. But it could also be many other kinds of engineers, because the biggest thing about engineers is they work together. So a civil engineer might need to consult, say, a mechanical engineer if they're trying to build a product like the Life Straw that we saw that they can put on shelves, and the mechanical engineer could actually design the product from the ground up. Or maybe they need an electrical engineer if that device includes, if it's a smart device, if it includes a charging port. So all these kinds of engineers work together. So these are the components that you guys are going to be using for your water filtration. And so you've got half cup of pea gravel, 15 cotton balls, 5 napkins, half cup sand. You've got 5 coffee filters, and then the actual murkiness that you're going to be adding to your water is a tablespoon of ground cinnamon and a pepper packet. And we had a couple questions before the lab started of should or could you be able to drink the water as after you filtered it? And we just don't recommend it because you guys are doing a model or a scale filter process. And so theoretically, if you get it completely perfect, there should be no pepper and no cinnamon left in the water. But just, for our sake, please do not drink the water and just dispose of it when you guys are done because we don't want any kind of sickness or anything happening. So here are a couple of hints for your guys' water filtration designs. Your group will build multiple filters to test with contaminated water. So make sure that you have a different couple of order of your materials, test each one, see what works, what doesn't work, and you will measure water clarity of each one using the rubric figure and container you have created. So you'll actually match the clarity level to this little rubric that we've included in the lab. Before building anything, think about how the water will flow through your system. And so I mentioned this a little bit before, try to get that water filtration rate, that flow rate, constant instead of maybe it clogs. You don't want it to clog because then at the end of the day, you don't have any clean water, even if your filter is super, super good. So try to balance that flow rate with your filtration process. You should pre-saturate and test your system with your clean water before using it with dirty water. So that means just pour some clean water through your system. And this is actually how you're going to test your flow rate and make sure you filter any materials that are washed out. So throw your water in there, let it pour through, and then you can see how good your flow rate is or how fast your flow rate is. Use the iterative process to improve your filters. So try to build one filter, see what works, what doesn't work, build another version, improve upon it, try to change a couple things. The more designs, the better, because the more designs you guys are able to perform, the more you'll learn about the filtration process. And then, of course, be sure to take photos of your before and after because we would love to see the results and or save a little bit of that before water so that we can see where you came from and then obviously your product at the end as we share our designs. All right. I'm going to play this video. It's a water filtration walkthrough, a little bit of a demo for you guys. All right, so you can see from this video that the water at the end was a lot cleaner than how it started, but there's still so much room for improvement. So we want to see if you guys can get an even better result than what you saw in this video. And then to analyze, we talked about you're going to look at the turbidity of your water sample. And so we've kind of thrown that word around, but what is turbidity? It's defined as the cloudiness or haziness of a fluid caused by a large number of individual particles that are generally invisible to the human eye, similar to like smoke and air. So the measurement of turbidity is a key test of water quality. Fluids can contain suspended solid matter consisting of particles of many different sizes. The World Health Organization states that drinking water should not be more than 5 NTU. NTU is that unit of turbidity. You saw that the water started out as 400 NTU at the beginning of that video. Ideally, it should be below 1 NTU. So strive to get your water below 5 NTU as a quality to qualify as drinking water. After creating your filter, try and find the turbidity of your water sample using this NTU chart. Your goal is to try to get 5 NTU or less. And then finally, we're also going to determine the economics of your design. So one of the biggest parts of engineering is having a cost-friendly solution that is affordable to the customer. There are many elements that impact the cost of your solution, but two of the most important ones are turbidity, how much cleaner the water was than your starting water, and flow rate, how much water can you process in a given time. In the event of a class competition to see who has the best filter design, both of these factors should be included. There is a cost penalty if your water isn't clean, but if your flow rate is too slow, you'll have to have multiple filters to get the same amount of water as someone who has a faster flow rate. So this is your added cost to your final design if your water isn't clear enough, if the turbidity is too high. All right, and that is our introduction, everybody. So a lot of the ideas and components that I talked about in today's breakout include osmosis and reverse osmosis, Stokes' law, which is actually a fluid flow law. I'm a huge fan of fluid dynamics. I study underwater motion. So Stokes' law is something that's found in fluid dynamics, clarifier design, the social impact of clean water, and fluid dynamics, name drop. And then the types of engineering that are involved in the clean water breakout are, as I said, environmental engineering, chemical engineering, civil engineering, and then actually material science. We need a lot of really good engineers to study what kind of materials are strong and what kind of materials have certain capabilities and aspects to them to help us with the water filtration process. So with that, I am going to stop my share and hand it back over to the main room.
What an introduction. I think you got them hyped up and ready to go, Lauren. I think they're ready. Thank you so much. We are going to get ready to open up these breakout rooms for you to get to work, purifying that water. We will meet back here at 11:30 for our Q&A and wrap up, where you can talk to our amazing college mentors and Lauren, and then you can show us what you've come up with. So we're looking forward to it. If you need any help getting into the breakout room, just let us know, and we'll see you soon.